Hello, my name is Arnold Filtser, and today I will tell you about the paper Hop-Constrained Metric Embeddings and their applications. Consider this graph and these two vertices U and V. U and V have many different paths between them. In the shortest path metric, the distance between U and V defined to be the weight of the shortest path between them of the minimal path between U and V, which in this case, this weight 14 path consisted of unit weight edges. Even though this path is have the minimum weight, it has some caveat, and specifically, it contains many edges. Now, this is something we like to avoid for different reasons. So first, in many scenarios, edges might fail and therefore it advantages to have less edges in your path, or as we will call it, less hops. Another reason, for example, in routing scenarios, might be the case that going to each vertex requires some processing time, and therefore it's also something that we would like to minimize. And so we'll define the h-hop distance, where the h-hop distance between U and V is the weight of the minimal path between U and V with at most h hops. So in this example, the 9-hop distance between U and V will be this red path that have weight 18. And you can see as we reduce the h in the number of hops we allowed in the path, the h-hop distance increases because we minimize over a smaller number of paths. Until here, the 2-hop distance is infinity because there is no path with at most 2 hops. So this is the h-hop distance, and we would like to study this distance in the context of metric embeddings. So a metric embeddings is a function between two metric spaces that maps points from x to points in y. So here we think, for example, about mapping the shortest path metric of some complicated graph into a tree. And we very much like trees because lots of problems become easy once you map them into a tree. We say that the embedding f has distortion t if for every pair of points x and y, the distance between them is distorted up to at most a factor of t in the image. So our goal in a sense to embed the h-hop distance. The major problem, however, is that the hop distance is not a metric. And this is a major problem. And indeed, it does not possess the triangular inequality. So note the following example. This is the end path graph. And the distance between the one hop distance between 0 and 1 is 1. Between 1 and 2 is 1 as well. But the one hop distance between 0 and 2 is infinity. So there's no triangular inequality. And therefore, in particular, this h-hop distance could not be represented by any metric in this case. Okay, so we still want to do it. To represent the distances somehow using a tree. And to make this possible, we introduce here 2 relaxations. So the first relaxation is we allow some slack in the hops. And specifically, we'll say that embedding f has distortion t and hop distortion beta if for every pair of points x and y, the distance between them in the image will be at most t times the h-hop distance between x and y in the graph, and at least the beta h-hop distance. So in a sense, we have different number of hops here. So this is the first relaxation. And the second relaxation that we allow to embed only a subset of the vertices. That is, you don't need to embed all of them, but only a subset. And using this relaxation, it will be already possible to obtain a nice result, for example, for this end path here. And so consider the set M to be the following subset containing all the vertices Vi, such that I is not 0 modulo 5. So in a sense, we just deleted all the vertices Vi such that I equals 0 modulo 5. And now this is simply the embedding, like the identity. So we get some forest here. And now we argue that it has this 1 distortion and hop distortion tree. We embed, of course, with respect to 1 hop distances. So note here, for example, if your 2 vertices coming from the same chunk, like this red chunk here, then the distance here is simply the identity to the 3 hop distance. So we are great with respect to like both of them. And from the other hand, if they're belonging to 2 different chunks, then the 1 hop distance is infinity, and in our forest also distance will be infinity, so we are good as well. So yeah, this is kind of Great. And know that there's actually nothing special about 0. If we sample I to equal some number s between 0 and 4, and let all the vertices which are which are s modulo f5, then we'll still get the same embedding with the same properties. But now each vertex will belong to this set M with probability 4/5. Okay, so yeah. So Hauffler-Hertz coefficient usage, they actually introduced these two relaxations and showed the first result in this context, which we called Ramsey time embedding, because you embed a subset. And what they show is the following. So given any endpoint weighted graph G and some parameter H and epsilon, there is a distribution D over pairs of MT, where T is embedding over M and M is a subset. So we have some distribution over like embeddings in subsets, such that for every vertex V, the probability that it belongs to the subset that we embed is at least 1 minus epsilon. This will embed almost all the vertices. And for every pair of vertices U and V that were embedded, we have this distortion guarantee. So the distance in the tree will be at most log square n times the H Hopf distance between U and V, and at least log square n times H Hopf distance between U and V. So we have here log square n Hopf distortion and log square n distortion. So here another example, this is the graph G, and we have this embedding into distribution over like trees over subsets. So in the first tree, both U and V belong to the subset. So we have this distance guarantee between them. In this tree, only V belong to the subset, and here only U. And the first contribution of our paper is just the improvement of the parameters here. So we get the same result, but the distortion will be log n, and the Hopf distortion will be log n as well. So this is a quadratic improvement in both the distortion and the Hopf distortion. And let me just mention that Hauffler et al. Used their embedding to obtain a bunch of bicriterion approximation algorithms for many Hopf constraint problems. So here we take some classic problem. So in this talk, we'll talk about the group symmetry problem, and you add some Hopf constraints, number problem becomes much harder, and you get some bicriterion algorithm when you kind of approximate the optimal cost and have some relaxation in the number of hops you allow. So we'll discuss it later. And we get some polynomial improvements in the cost and the hops somewhere. Yeah, so we'll discuss it later. And let me also mention that we actually get the generalization of this result. So while here we allowed only for log n distortion, you actually can get much smaller distortion for every parameter k. You can get distortion which is asymptotically k, and the Hopf distortion also changes accordingly. And the caveat, of course, is that the probability now to belong to the set is much smaller. Instead of like 1 minus epsilon, almost everybody belong to the set M. Now your probability to belong to the set M is only n to the minus 1 over k. Next, I would like to show an application to compact routing schemes. So this problem, we having a huge network, and in each node in the network, there's some server. And these servers want to route some packets between them. However, the problem is that the network is huge, so it's completely unfeasible to store the entire network in each node. So more specifically, we have some initiating node who has some label of destination, and he wants to send a packet. In the middle of the process, consider this node, he gets a packet which contains the label of destination, some content, and it has some local routing table, and based on this local knowledge and the label of the destination, it's need to decide where to send this packet next, and eventually this packet should get to the destination. So this is the problem. In the Hopf constraint version, in addition, we require that the overall number of hops between in this path this packet has from start to end, there is most h hops. So just to see this problem kind of very central, and indeed there's hundreds of paper which having these words Hopf constraint routing. However, this paper now is the first one to give any provable guarantees on the Hopf constraint compact routing. So our result is the following. For any n vertex graph G and some parameters k and h and epsilon, there is a routing scheme with label size of k log square n. This is the label size here. And the table size, the local knowledge is k times n to the 1 over k. So discounted in words. And the guarantee is that for every pair of vertices nodes u and v, the packet will be routed on a path P with at most h times the k square times log n hops, and the weight of this path will be at most some constant time k times the h hop distance between u and v. So there are no previous results, but just to compare with the state of the art of the non-hop constraint problem, so Chechik get in sense the same stretch up to this 1 plus epsilon, and here we lose only a log n factor in the size of the label in the table, and we get this hop constraint guarantee. Next, I would like to discuss one-to-many embedding. So in the Ramsey type embedding that we discussed earlier, the major caveat was that you embed only a subset of the vertices. This is a problem for some applications. And here is kind of a way to overcome this issue. So in one-to-many embedding, we embed each vertex to a subset of vertices in the image, not a single, like in usual embeddings. So in this example here, this vertex 1 is mapped to 2 vertices, and each such vertex is called a copy of 1. 8 is mapped to a single copy, and 19 have 4 different copies. We require that this embedding will be dominating. That is, for every pair of vertices x and y, and for every 2 copies of them x prime and y prime, the distance in the tree between x prime and y prime will be at least the beta h hop distance between x and y. This embedding should be onto. That is, all the vertices here are pre-images of some vertex, and also every vertex has a non-zero kind of map. You cannot be up to an empty set. Each edge in the tree will have some associated path between the pre-images in there. So like 10 and 20 has some map, some path here, which is associated with this edge. This edge has a simple path, single edge, but this edge here, 113, has quite a long associated path. Further, given 2 copies, u prime and v prime, which are not neighbors, there's a unique path between them in the tree. And then we define the associated path with this pair, this pt u prime v prime, to simply be the concatenation of the associated paths along the tree. So here we have like, this is the path associated with the first edge, the path with the second edge, the third and the third. And so this will be the path associated with the pair of copies 20 and 16 here. And we say that the one-to-many embedding F has hop bound beta if for every pair of copies u prime and v prime, this path associated with them has at most beta hops. Okay, and finally, we say that a one-to-many embedding F is th subgraph preserving. So this is the most crucial property. If for every subgraph S of G, like this purple subgraph here, there is a subgraph S prime of T of weight at most T times, so this is this T, the weight of the subgraph in G, and such that for every pair of vertices U and V in the subgraph S, such that they have some path of at most H hops between them, the subgraph S prime will contain some copy of U and some copy of V in the same connected component. Okay, so for example, here we have this purple subgraph, and we set H to be 1. So in the subgraph S prime, we need that every pair of vertices with 1 hop distance, like distance most 1 hops, will have copies in the same connected component. So like 1 and 18 have here copies in the same connected component, 18 and 19 has here, but it's in the same connected component, 19 and 13 is here. So now that 19 has several copies in the subgraph S prime, and 13 and 17 here. Now, once we increase H to be 2, now 18 and 13 should also have copies in the same connected component, and this happens here. And in H equals 3, we already have a single connected component in the image. Our embedding result in this context is our hop constraint subgraph preserving embedding. Here, we are given an endpoint graph G, some hop parameter H, and a vertex R, special vertex R, and we construct a dominating one-to-many embedding F into a tree T with associated paths for each edge, their associated path, such that, so first, the overall number of copies, the overall number of vertices in the tree is at most some small polynomial, and the special vertex R has only a single copy. Next, F has hop bound at most log cube n times H, That is, the associated path of every pair of copies has at most log cube n times h hops. And finally, F is log n h subgraph preserving. That is, every subgraph in G has some subgraph in the tree with similar rate and such that vertices which are closed in the hop sense in G have copies in the same connected component in T. Okay, so this is the result. And let's see an application of this subgraph preserving embedding to the group symmetry problem. In the group symmetry problem, we are given some depot vertex R and subsets of groups G1 to Gk. And the goal is to find a tree of minimum weight spanning the vertex R and list one vertex from each group Gi. So this is an example of a valid solution. In the hop constraint version, there is in addition a hop parameter h. And the goal is to find a tree spanning the vertex R and H group Gi such that the distance, the hop distance, I mean the number of hops between R to any group Gi in this tree will be at most h. So in this example, the parameter h is 2. So this is no longer a valid solution because the path from R to this purple set has 4 hops. But this is a valid solution because now the distance from R to every group has at most 2 hops. So this is the problem. Garg, Konjev, and Ravi constructed a log square n log k approximation algorithm for the group symmetry problem. So this is the classic problem. And our solution, our contribution is a bicriteria approximation for the hop constraint group symmetry problem. And specifically, we constructed tree T with weight at most log square n times log k, the optimal solution. So this is the same approximation factor as Garg et al. And this is bicriteria because we only guarantee that the tree T will contain a path from R to every group of at most log cube n times h hops. Okay, and just to compare with Filtser et al., they obtained similar result, but the weight of the tree was log to the 4n times log k. So we get a quadratic improvement here in the dependence on n. Let's see how we get it. So we get some instance of the problem. And our first step will be to use this subgraph preserving embedding and embed the graph G. So this is the graph we get the groups, we have the special vertex R, and we embed it into this tree T using a log n 2h subgraph preserving embedding. Okay, now we define the problem in the tree. So for every group Gi, we'll define a group Gi prime, which will simply the union of all the images of all the vertices in Gi, and the depot R prime will be simply the only image of the vertex R. Consider an optimal solution to the problem S star. Now, because this embedding is subgraph preserving, we are guaranteed that there's some S star T in the graph G, in the tree T, of weight at most log n times the weight of S star. And note that this is a valid solution because here the hop distance between any group to the depot R was at most h. And therefore here we all be in the same connected component. Now, Garg et al. Constructed the log and log k approximation algorithm for the group symmetry problem in trees. So this is just a tree, no hop constraints, so we can use Garg et al. And we find some valid solution in the tree as tilde t of weight at most log n log k times the optimal solution, which by itself has at most log cube n log k times the optimal solution in the graph G. Okay, so we find some nice solution. And the final step is to pull the solution back to the graph G. And we do that by simply taking the union of all the associated paths of all the edges in the solution S tilde t. Okay, and this is the final solution. Now note that the weight of S tilde is at most log square n log k times the optimal solution. And we also have the hop bound because the hop distance between the vertex R to every vertex vi here will be at most log cube because I mean there is some associated path in the tree T, and because f has small hop bound, we guaranteed it will be small in the graph G as well. So that's it. We got our bicriteria approximation for the group symmetry problem. So just to wrap up, in this paper we have 2 major embedding results. So first was this Ramsey type embedding, where we have this kind of approximations between like hop distortion and distortion, and only subset were embedded. And the second one was this subgraph preserving embedding, which is come to be very handy. That's it. I hope you enjoyed, and thank you for listening.